Far East, the Middle East and Europe. Our core skill set is facades, but we also provide component services such as building maintenance, building physics, acoustics and facade lighting. Just a snapshot of some of the projects we're involved in. Can't quite see from this angle, but you can see we're involved with sort of super high-rise, free-form parametric geometry buildings, and then your more standard commercial retail buildings, etc. around the world. In the Middle East, our portfolio tends to be very commercial type buildings and retail, some residential as well. And I think in Qatar, the major project we've been involved in would be the Qatar rail stations. So today, I'm going to talk about basically efficient design of tower facades, and maybe have a look at some of the construction and installation aspects of that. And then I'll finish off talking about maybe some of the new materials that can be used on the facades maybe going forward into the future. So I think what's become apparent to us over the years in high-rise design is there's two very distinct phases in facade design. There's the pre-tender design phase, which the consultant team, the architects, the engineers, the clients are involved with, and then the post-tender phase where it's then designed in detail by the contractor. And really a successful facade will come about if you manage to execute both of those phases well. So one thing we did, I mean this is about 8 years ago, we started actually recording efficiencies in the pre-tender design, what we thought was an efficient design pre-tender, and what was an efficient design post-tender, to really understand what are the drivers, what are the mechanics to come up with an efficient, sustainable and cost-effective facade. So these are projects in Dubai, and the dark green lines, the higher the line, the less efficient the facade. So we're really looking for short lines in this image. So the dark green lines are post-tender, and the light green lines are pre-tender. So I'll just go through basically how we look at the design efficiency. So if we look at pre-tender, we basically look at the allowable mullion depth. Now that affects the interior space, GFA calculations as such. The mullion spacing, that's how big your apertures are going to be to see out. And the wind load, which of course we have less control on. And then post-tender, when we've defined this overall mullion shape and spacing and size, it's how efficiently can the contractor design the aluminium or PVC to fit in that envelope, that size we've given, whilst taking care of the structural, the waterproofing, the acoustical requirements, etc. So I've just picked three projects from this case study here, and you can see on the left one, Park Place, had a reasonably efficient design planning, but an inefficient design detail post-tender. So the mullion spacing and size was quite reasonable, but because the facade was a warped facade, as opposed to adopting a cold bent type solution, the contractor decided to facet the panels. Now this created a lot of additional aluminium, which was not doing anything other than aluminium like here, other than forming an architectural enclosure. So there's a lot of wastage in the design. Conversely, on the right side, the design was very efficient by the contractor, but the mullion space that the architect, the facade consultants gave was too small. The mullions were 3-meter spacings, the wind load was high, and the allowable depth was the same as the project on the left almost. So that ended up, although the contractor did his job very well, it still ended up with an expensive design. So what we're trying to look for is, as I say, a well-planned facade, which is the one in the middle, where we allow sufficient space for sufficient size, and then we work with the contractors post-tender carefully to make sure we get an efficient execution. One thing that affects the size of the mullion and the amount of aluminium you require, a lot of people are maybe not aware of, is the height of the stack joint. So this is the horizontal joint. Sorry, it's not very clear. The laser's not strong enough. It's the horizontal joint which separates one panel from the panel above. Now, typically you'd expect, or intuitively maybe, you'd expect the most efficient position to be at the floor level. In fact, it's not the case. It's actually more efficient to have the stack joint slightly above the floor level. Now, this has architectural implications, so this is where we have to work very carefully with the architect to balance architectural requirements with cost and efficiency requirements. So these are just some plots showing how the area of aluminium will vary depending on what height you position the stack joint. To put this into context, I'll show you a project we worked on in Vietnam. And originally the stack joint was at the floor level. And, oops, sorry. Which way am I going? Sorry. So you can see here that the stack joint was at floor level. Now the bottom panels are all opaque, so there's absolutely no architectural implication for raising the stack joint up. So by raising it up, we got significant, 40% reductions in material, about 9% reduction in depth. I'll just go through now briefly a tower we've been working on for the last couple of years. It's just started construction now. Sorry. So this is Entisar Tower. It's in the centre of Dubai. You can see it here, just about. So it's a super tall tower. It's about 520 metres high. So obviously we're looking very carefully at efficiencies given scales of economy. The first thing we wanted to do is we wanted to look at panel sizes. We wanted to minimise the number of panels due to installation. Now there's a trade-off between panel size and how heavy it is to lift and how heavy it is to manoeuvre. So we started off with some sketches. A typical facade panel would be about 1.5 metres wide by a floor height. We wondered if we could go bigger, maybe 3 or 4.5 metres. So from these sketches we started building models and we started calculating how much aluminium, how much glass would be required in each case and how it would affect the architecture. So you can see we now start to create a number of different variables. This is the parametric design we've been talking about before, where you can start off with 2 or 3 variables and generate a lot of different options. So we have 4.5 metre wide modules and 3 metre wide modules. Eventually we chose the 3 metre module for cost and installation. And then after that we wanted to look again at the stack joint. So from all of these options we have here, we then have another 4 options, or 4 variables, which gives a further set of permutations. Finally, we start discarding. We can see which ones are not going to work, and we start shortlisting the ones that will work from a cost, aesthetics, and installation point of view. So these are shots of the analysis of, in terms of the aesthetics and the architecture. We looking very carefully at how much light and how much heat we're letting in, and how many opaque and how many clear and how many semi-opaque components we're going to use in this facade. So when we've got the modulation fixed, we then start looking at, okay, what's the light and thermal transmission properties of the facade we're going to look at. And these are some images of studies we've done for glare inside and thermal studies to check that that's all working given the extreme climates we have to deal with here. Mullion shapes, the final thing is really the shape. Traditionally, rectilinear mullions are used. It's actually very easy to use curved mullions. We're recommending these on a number of jobs because the sight lines are much less. So it depends on the architect and the client, his visual aspirations, but it's something that's becoming increasingly common to give sort of softer, less obtrusive mullions. And then where are we going in the future? Well, some of the studies we're looking at in Australia is actually to reduce the aluminium further. Aluminiums are very expensive and also a very energy, a costly material to use in terms of energy usage. So we're working on several projects where we're looking at actually reducing the amount of aluminium down. Now, aluminium's still very useful because it's very good to form and provide watertight seals. So we're wondering if we can marry the aluminium with other elements such as timber to form the structure, but keeping the aluminium at a reduced rate to form the water seals on the building. Right, I'll talk about construction a little bit now. So, unitised curtain walls, I'm sure most of you are aware, are all fabricated off-site and lifted in. So, when you're deciding to use a unitised curtain wall, you're getting two benefits. You're getting factory fabrication, high quality, and hopefully you're getting fast installation, which frees up your interior fit-outs, speeds up the construction programme. This is a shot in Dubai Marina when I first arrived in Dubai about 10 years ago. And this is not conducive to a good facade installation strategy. You can see there's many appendages on the outside of the buildings. There's tower cranes tied back. There's rubbish chutes. There's lots of catch fans. So lots of appendages. Each of these appendages interrupts the installation of the unitised curtain walling and actually slows down the construction significantly. So here's some typical projects I just found on the internet. Middle one and the right one are in Hong Kong. That was about 2007, I think. And the one on the left is Freedom Tower in the States. Now, I think it's you can see how much less paraphernalia they have on the outside of the facade. So I think one thing we're pushing going forward is to try and work with the main contractors to try and reduce the amount of construction materials or techniques they have, and try and implement some that have been used elsewhere in the world. Things like having the tower crane in the centre of the core, using jump lifts in the lift cores. All of these things can take appendages off the perimeter of the building and actually speed up and more importantly, make more safe the installation of the facades. So here's some shots just to explain how facades are typically installed. So a typical unitised, they'll typically bring panels in every 10 floors. So they'll either by tower crane onto loading platforms, and they'll store the panels every 10 floors roughly. They'll then use either monorails or mini cranes to then drop those panels down, panel by panel, to a floor lower down where they're actually being installed. So we're working with two or three contractors at the moment and actually using slip form construction. So actually using the climbing formwork to be used as actually an installation platform for the facades as well. So this can be very, very efficient in terms of the facade actually climbs up with the formwork. The critical thing is obviously we have to have very good program management to make sure we have the panels on site ready for the formwork. If you've got delays in your panel fabrication, then you're basically slowing the whole construction down, including the floors. But it's something that several contractors are looking at now, particularly on super high-rise towers. So here's a section through. Sorry, the laser isn't strong enough really, but you can see that basically there's a monorail on the bottom of the slipform which actually hangs the panel, and then as the panel can then be dropped down and installed just underneath. So as this slipform goes up, 2 floors or 3 floors behind, the panels are being installed. Here's a blow-up of the actual, showing the methodology. So you can see the top floor is the monorail, and the floor below is actually where they'll be installing the panel. This is something else that we've been trying to promote in the Middle East. Pretty much every project I've been involved in has got this type of cradle, the one on the left. And they do have protection rollers, but they're not sufficient really to stop the scratching and damage of facades. So we spend all this money on expensive glass and high performance sustainable designs, and then we buy a very cheap cradle and everything gets scratched. So the idea we've taken is actually, this is a cradle that's been used in London, and for me it's interesting. The cradle was actually designed because they were more worried about an impact safety, and from our opinion it's complete overkill in terms of safety. You certainly don't need these buffers to make the facade more, the cradle and the facade more safe. But what it does do is it does prevent scratching, and it's a very cheap and cost-effective way of preventing scratching. So that's something I'd recommend contractors, developers all to consider, because it's a very cheap, simple thing to do, and it can really help improve the long-term quality of the building. We're always looking, sometimes the most complicated solutions aren't necessarily the best in our opinion. So this was a project I was involved in Abu Dhabi, Central Market. So 2 pretty big towers. And the architect had the concept that he wanted every single piece of glass to be removable in case one broke. Now, to put these into context, these panels are about 2 meters by 4 meters pieces of glass, and you're trying to remove and replace one 300 plus meters in the air. So we designed it, and it was a very interesting technical challenge to create these very sort of Swiss watch engineered cassette systems which allow these glass panels to be unhooked. But the end result was that you probably had about 25% more aluminium in the system, and more chances of water leakage, because where we have these cassettes that can be removed, there's chance of air and water getting in. So sometimes I think it's good to step back, and rather than design every panel on the building for the case of 4 or 5 panels breaking, we should be maybe looking at the maintenance solutions more. So why not design a cradle that can give a full factory environment to fix the 1 to 5 panels that break in 10 years, as opposed to chucking 25% aluminium on the whole building. So I think our message in the Middle East is a lot of the time we get, we work in Europe and we work in the Middle East, and the scale of the buildings in Europe compared to the Middle East is generally, from my experience, much less. Most of the projects are much smaller in size. They're very, very high quality, but the overall size is less. So it's not necessary that just because you have something that's been done in London, it's immediately transferable to a market, or it's even better, it means it's better quality to be done in the same way here. Okay, so I'm going to finish up on maybe something slightly more interesting or lighter. So some of the new facade designs or materials that we could use. First slide I'm just showing is really how things have changed since I've been here over the last 10 years. So traditionally, there's the discussion about we shouldn't have all glass buildings, which I totally accept. But I think what's interesting to me is if you look on the building on the right, it's very reflective, it's very dark inside. And if you look on the building on the left, it looks much more aesthetically pleasing, and it's much more transparent. Now, in terms of energy, both of the buildings are letting in the same amount of energy. So it's quite phenomenal how much glass technology is improved. I think the next stage is really to start using shades in a more effective manner. But I don't see the glass technology going much further than it has already in terms of reducing energy. Cold bent glass. So this has now become quite the norm. I think the Middle East has probably got more cold bent buildings than anywhere else in the world. So this is where we basically build facade panels flat, and then we physically force them into a three-dimensional curvature on site. So this is a very cost-effective method of achieving, the new parametric three-dimensional designs that are now available with the new computers we have. So I think that's good news. It's not necessary that if you have a free-form double curve geometry, it's going to cost exponentially more if it's designed in the right way. So we can use techniques to design the facade panels flat and then just physically bend them on site, which means you haven't got any special material or extra cost. Switchable glass, which I think Lars mentioned. So a couple of projects that are in design in the Middle East at the moment, which is using this. This is from Sage Glass in the US, which has now been bought by one of the bigger suppliers. I can't remember which one. Honestly, I think it might be Saint-Gobain or Glaverbell, one of the two. But I think this is very useful for the Middle East. So early morning, you can have very clear glass with a relatively reasonable shading coefficient. And then as it gets to midday, as it gets hotter, you can actually reduce the light transmission and also the thermal heat gain. So these glasses are switchable in 3 settings, so you can see. Now that could be either done manually or it could be integrated to a building management system. So you could connect that to a temperature sensor or such, so the glass could actually respond to the climate conditions. Another one we're looking at, thermochromatic glass. So this is similar, but it's more passive. So this glass will actually change depending on how hot the surface of the glass is. So the same thing, but it's not actively managed. Fritting has come on a great deal, I think, recently. There's several processes in the Middle East now that will do digital printing, which means you have a much greater array of colours and patterns. You can print pretty much anything now. Coloured glass is improved as well. We can see we can get these pastel colours now, which weren't available probably 10 years ago.